Hello everyone. Today we will be presenting our DA422 course project on investigating layer-wise polynomial degree assignment for fast private inference in homomorphic encryption. I am Shrutee Prakash Dalai and I'll be giving the overall introduction of our approach. We know that fully homomorphic encryption or FHE is the holy grail of privacy. It allows us to run machine learning inference directly on encrypted data without ever decrypting it. However, there's a catch here. FHE is incredibly slow. A major reason for this latency is that standard neural network operations such as ReLU and max pooling are not polynomials, so they aren't natively supported. We have to replace them with polynomial approximated function, or in short, PAFs. In this project, we reproduce the results of a framework called SmartPath, which helps train these polynomial networks. But we also asked a new question. Do all the layers in the neural network require the same polynomial precision? We discovered that they actually do not. Specifically, later layers are much more sensitive to approximation quality. Our experiments showed that the assigning lower degree polynomials to early layers and higher degree polynomial to later layers, that is a low early and a high late configuration, actually improves accuracy compared to the reverse case. Next we come to the introduction. So what exactly is the need of privacy and what's the FHE bottleneck? Let's dive into the details now. Machine learning is being deployed in highly sensitive areas nowadays, such as healthcare, facial recognition, and finance. Protecting this data is critical. The solution. FHE offers a solution by enabling computation on encrypted data itself, protecting both the user's input and the model's parameter. But this security comes at a cost. FHE inference can be up to 5 orders of magnitude slower than standard inference. Why is it so slow? Because popular FHE schemes such as CKKS only support addition and multiplication, and they do not support non-polynomial operators like ReLU. To make a standard neural network work in FHE, we must replace every ReLU with the polynomial approximation. This creates a trade-off. Higher degree polynomials give us better accuracy, but they require more expensive multiplications, which drastically slows down the system. The smart path approach in general. To solve this, we looked at the smart path framework. It introduces techniques to make low degree polynomials, which are faster, actually converge during training. It uses methods such as coefficient tuning and progressive approximation to achieve competitive accuracy with much lower latency. Now, what exactly is our contribution here? While SmartPath is impressive, it applied a uniform polynomial degree across the entire network. We realized this leaves an important question unanswered. Is the sensitivity to approximation error the same at the first layer as it is at the last? Our first contribution is on reproduction of the SmartPath. We successfully reproduced the SmartPath pipeline on ResNet 20 using the CIFAR 10 dataset, validating their training techniques. The second contribution, which is basically the new method, we proposed the novel extension of layer-wise degree assignment. Instead of using one polynomial everywhere, we split the network into groups and assigned different polynomial degrees to earlier versus later layers. The third contribution was the analysis, or specifically the empirical analysis. Finally, this confirmed that the later layers do benefit significantly from high degree polynomials. Specifically, our low early high late configuration outperformed the reverse by 0.32%, suggesting that in FHE systems we should save our computational budget for the deeper layers of the network.
Okay, so hello, myself Uday Jain. I will start explaining the code written. So first of all, this is lib.py. It has all the necessary imports, including all the different kind of torch imports we need. Then we have the util.py. So if you see, like here, I wrote the different data loader functions. So whenever we load an image, we also crop the images randomly, so that and then we even flip the images. So this provides us with a better data set. Finally, we normalize all the images data, and then we also create the validation data set. We only normalize the validation data set because like we are kind of testing out there. So, and then I wrote this function to get the all the data from the data loader. Yeah, and then there is this. I wrote this resnet model.py. So if you see here, like I first wrote this basic block. So this is the basic building block for the neural network. I defined the various convolutional layers and all the different activation functions here. Then I wrote this forward function for the basic block. Then this is the Cipher ResNet class, which is like the actual ResNet, uh, which you takes the block as the input. And if you see here, like yeah, you can see that the Cipher ResNet actually takes the basic block as the input. So then like I made the various layers required, and then wrote the forward function for the corresponding Cipher ResNet as well. And yeah, then I finally actually made the ResNet, and I also wrote the function to actually import the model if we already have the weights. Yeah.
Okay, so I'm Parth Agarwal and I'm going to explain going forward. So yeah, this is custom module.py. Here I have defined different functions. So prior to coefficient tuning, we need to collect various intermediate activation values. So as you can see, these are the functions to collect data and the scale of different layers. So here you can see the scale is being collected and then it is being saved. And going forward, here are the various functions. So what the paper does, it approximates nonlinear activation functions using polynomials. So here I have written all the code for the polynomials. This is for all the sign min max layers. So here you can see there's the degree of the polynomial, the coefficients of the polynomial, and this is just to find the appropriate parameters. Similarly, this is for here in this function, the code for polynomial approximation of sigmoid layer has been written. Similarly, in next, here's for the ReLU layers. Here it is for the CLU layers. Now going forward, there is code for the max pool layers. And yeah, that's all. So going after that, this is the code for the coefficient tuning. So after data collection, the first step is to tune the coefficients. So this is a script which does that. So here I have written the parser which parses the argument. So here is the sign type, which is the polynomial we are using. So earlier in the paper, only a singular degree type was being used. So I modified it, and now two different values can be passed. The first value would be used for the first half layers of the model, and the second polynomial approximation will be used for the second half of the model. So this is the parameter to specify if we are currently in data collection phase or not. So after that, here is the if we are currently in the data collection process. So this function basically calls the part for data collection, and so you can see here's the data collection function, which one by one calls data collection for input, and after the data collection process is done, the next step is to actually make the coefficient tuning. So this is the code which does that, and yeah. After that, after coefficient tuning, the next part is progressive approximation and alternative training. So this script achieves that. This is the code to log different things which are going on during the training process. This is the optimizer code. This is to test the accuracy. This is just the code for the loss function, and yeah, here the complete trainer has been defined. So this is a function to save the model. This is an individual training loop, you can see. After the loop calls basically train epoch function which trains a particular epoch. This is the function for validation because earlier, as we had told you, we have created a validation dataset as well. So yeah, after progressive approximation is done, the next part is to just simply rescale and do the static scaling. So this is the script which achieves that. So I have written this function which just finds out the scale and then resets the scale using a CT reset scale and a scale replace function. So yeah, so this is the complete code which is there to run the model. Now I'll show you the steps which have to be followed. So first of all these commands should be run from the src folder, and the Sifat and datasets should be present in this folder named datasets in the same directory as the src folder. So the first step is going to be data collection. To run that, you just have to specify the script that you are running, which is ct.py for data collection, the working directory in which all the intermediate values will be stored, and make the data collection flag to be true. So after that, this file would be populated with the intermediate values for the validation and intermediate values for the train. So this file is going to be pretty big. It will be roughly 100 GB in size. And after the data collection process, you have to uh, run the CT script. This time we are not doing data collection. In ST, you can specify the polynomial degree you are using. This is if you want to use the same polynomial degree for all the layers, and you have to specify like this if you want to use different polynomial degrees. And after running the CT script, the next part would be to just run the progressive approximation script. And once this has been run, the final step would be to run the ss.py script, and after that the model has been trained. And you can check the accuracy. We have provided that in the paper. So yeah, thank you.
I'm Kratika Pal and I will be explaining the conclusion, limitations, and the future work. This project successfully evaluated the SMART PAF framework and extended it to test a novel hypothesis about layer-wise precision. Our experiments confirm that not all layers are created equal. The low, early, high, late configuration achieved 88.73% accuracy, beating the reverse configuration by 0.32%. The impact: this is significant because it proves we can optimize the latency accuracy trade off. We don't need high degree polynomials everywhere, we just need them in the right places. Coming to the limitations, it is important to acknowledge the limitation of our study. We originally planned to test this on the larger VGG 19 model. However, this has significantly more non-polynomial layers than ResNet 20, which would have required training times exceeding over our available computational resources. Similarly, we were unable to extend our testing to the CIFAR 100 dataset. Due to this, some constants focusing strictly on ResNet 20 with CIFAR 10. While we measured theoretically complexity, multiplication depth, we did not run benchmarks on an actual FEH backend to measure wall clock latency savings. Let's next coming to the future work. Moving forward, there are exciting avenues for research. First, we should explore finer grained assignments. We only tested two large groups. A layer by layer optimization search could yield even better results. Second, validation validating this finding on larger models and more complex datasets is crucial to prove that this late layer sensitivity is a universal property of deep networks. Next, finally, the ultimate test will be implementing this logic in a real FHE compiler to quantify exactly how many milliseconds or seconds of inference time this asymmetric approach saves. Thank you.